Hello, I'm Anna Bolotina, and I'm going to tell you about our work on developing composable sequence macros for fast iteration in Racket. This is a joint work with Ryan Culpeper performed at Czech Technical University in Prague. So first, I'm going to tell you what our paper is about. Specifically, we're working in the context of the Racket programming language, and the problem that we're solving is that we generally want a better way of expressing sequences in Racket. First of all, in Racket, there are two kinds of sequences that can be used in for loop clauses and control iteration. There are dynamic sequences like lists, vectors, or ranges that implement the generic sequence interface that is dispatched at runtime. And there are applications of sequence macros like in-list or in-range that we call fast sequences, as they are dispatched at compile time and thus allow the compiler to apply additional optimizations such as inlining. But a fast sequence is only treated specially if it is used in a fast sequence context, such as the right-hand side of a clause, of a for clause. Otherwise, it acts as a dynamic sequence. There are also ways of composing sequences in Racket, like applying mapping or filtering. Consider the task of defining an abstraction for a sequence of squares of prime numbers up to some n. The simplest solution is to use lists with list-specific combinators. This solution has a downside. It eagerly allocates a big intermediate list. That can be avoided by using the sequence macro in range along with generic sequence combinators. The sequence produced by in range is lazy, but here in range is not used in a fast sequence context because sequence filter is an ordinary function, so it fails to improve performance. What we would like to have is a nicer way of expressing sequence abstractions in Racket, like having fast sequence combinators that would be sequence macros by themselves, and their second argument is a fast sequence context. In this paper, we define such fast sequence combinators for mapping and filtering that we call fast sequence map and fast sequence filter. And now we can express our sequence abstractions like abstraction like this. So now we eliminated both of the downsides we had before. We then also define a generic purpose form called doSequence in Racket for loop style, for loop-like style syntax that supports mapping, filtering, and nesting of sequences. And I will have an example of nesting later. Using doSequence, our sequence abstraction can be rewritten as this. Our work is motivated by Racket libraries that can benefit from fast sequences. One such example is a data frame library that defines an in-data frame sequence as an ordinary function, and it can be concisely rewritten using the doSequence form to act as a fast sequence. Another motivation is the fact that we should be careful about scoping when defining our macros using Racket's API, and we should worry about their specification. And an example of that is coming soon. Now I'm going to talk about how this works. And I should note that we are working in the context of Racket macros. They're the tools that make available the generation fast. It's not done by the means of compiler support or type systems. The syntax of a for loop in Racket contains clauses and a body. A clause contains a list of iteration variables and a sequence expression. In Racket, for is not a primitive syntactic form, but a macro that expands into a call of a recursive function, as it is illustrated by this example. That function is formed by three parts. Firstly, its shape is dictated by the variant of the for expression, for example, for or for sum. Secondly, it uses the information that comes from the for loop clauses, namely about how to start looping, how to decide whether to stop looping, what values to bind to the iteration variables and auxiliary variables, and how to recur. Finally, the third part is the for loop body. The first part is a loop skeleton which comes from the for loop variant and has blanks. We consider the expansion of for, and for it tells the following structure where the blanks are highlighted. The second part is a compile time record for each for loop clause. For example, the clause x in list 1, 2, 3 has the following intermediate representation. This intermediate representation is called an expanded closed record, or an ECR. Consider mapping a list of numbers with square. We would like to implement it by simply adding another inner binding for the squared value like this. But the right-hand sides of the inner bindings are not in the scope of previous inner bindings because of the semantics of flat values that the loop skeleton uses. So this solution is not correctly scoped. We can fix the scope by combining the bindings into one that binds all of the inner variables, and by using nested flat values like this. And the expression of the for loop for this example is the following. Now consider an example of filtering. The for expression in this example has two clauses that are iterated over in parallel, and to get the correct result, it should filter the values of the list of numbers in an inner loop. Here's how the ECR for the second clause in this example looks. And we can see that it is more complicated, so we should be careful about keeping its scope correct. And it is a complicated enough problem, which is the second motivation of our work. So we should worry about the specification of our macros, and in particular of an ECR. The scope and structure of ECRs is established by the loop skeleton, and where it places the identifier and expression components of the ECR. For example, the postguard expression is in the scope of the loop IDs, but the preguard and loop arc expressions are in the scope of both the loop ID and the inner IDs. These are scope and obligations for our transformations that our transformations must satisfy. We can manually check them by expecting the general form of the filtering transformation. Given a predicate pred and an ECR in, the filtering ECR is the following. And here is an example of a specification of ECR using a notation that we invented for checking the scope correctness of our macros. So it's not a contribution because we haven't formalized it, but it helped us to think carefully about scoping. Now consider an example of a nested iteration. Consider a custom hash set data type represented by a structure containing a hash function and the vector of lists, where the hash function determines the index in the vector where an element is stored, and each vector slot contains a list of elements to manage hash collisions. For example, the set 3, 12, 35 could be represented thus. Now suppose we want to print the elements of the set S. We can do it like this. But with the combinator for nesting, we can define it as a sequence abstraction, which is reusable, and then iterate over it. And we define this combinator in our paper. So here's what we've accomplished. We've built fast sequence combinators for mapping, filtering, nesting, and a generalized form. One non-contribution is our notation for macro specifications. Also, another thing that we've discovered is that the clean idea of type system support isn't enough to solve the problem by itself. There was a more complicated problem, and we had to go to Racket's macro support. If you want to know more about it, Ryan can explain it in Q&A. Also, we have benchmarks that show that our macros are much more efficient than dynamic sequences and are close enough to the solution using sequence abstractions and to hand-optimized solution. They are a bit slower due to some limitations of the ECR representation. Another result is expressiveness of more macros. For instance, here's an example using the Sozal library that builds on data frame, and it can be implemented using our macros in a practical and useful style, almost without changing the original interface of Sozal. And our benchmarks show that it is also fast. And we have 18% of speed up compared to the dynamic implementation. This is the end of my talks. Thank you for listening.
Thanks. Now, all right. Anna, can you hear me? All right. So we can take questions. I'm not sure. Okay.
So thank you for a good talk. And you have been using Racket specific syntax all the time. And so there are a bunch of research in other, using other languages such as, Metal Camel or Temporal Haskell to generate programs where, binding and the scopes are the most problematic problems, and there are a bunch of different type systems to ensure there is no scope exclusion and so on. Can you, maybe it's difficult to answer, but can you compare your work with, the works done in other programming languages?
Let's wait for
It's
an answer to come
difficult
up.
to guess. Well, she understood my question or not.
Yeah.
Yes, he can answer.
Yeah, if you do Slack, then you can see someone is typing. It's going to be a long response. Yeah.
Anna, did you understand my question?
Maybe you type QQC.
Type my question.
No.
Okay. Yes. Oh, yes.
Of course, if she's in the middle of a long
Yeah,
response,
but
then she-
even so, she can.
Oh,
Yeah, I know. I'm so sorry that you can't speak up.
Yes. She is macro. I want to ask a few more questions.
Okay, so we didn't make a comparison to other languages, but we compared our notation for scope correctness to the Romeo language for specifications like ours.
So
It,
they compared. Well, okay, yes.
Are you satisfied with the answer? Or-
Yes. Okay, you can come up to the microphone.
So thank you for the talk. I was wondering if you measured the size of the generated code and you found that it was still reasonable in some of the larger examples, like when you drop in replacement for Sawzall. I wonder if the size of the generated code started to matter. or if you looked into that. We didn't measure it for Sawzall, but I think it only starts affecting the performance for applications of our nesting form with many levels of nesting. That makes sense? Yep.
Thanks.
Okay.
Okay.
Thank you.
Maybe we can take one another quick question. If not, okay. Thanks, Anna. And